research chair at the Perimeter Institute of Waterloo. Now he has been given many honors and awards, so I'm just going to point 4 of them. So the first one was in 1991, he was elected Fellow of the Royal Society. In 2000, he was given the Paul Dirac Medal and Prize of the Institute of Physics. In 2004, he was given the Larson-Sager Prize of the American Physical Society. And I quote here, for his profound and original applications of conformal invariance to the bulk and boundary properties of two-dimensional statistical systems. In 2010, sorry, you have too many prizes. I mean, I get lost in the list. In 2010, you received the Boltzmann Medal. I think it was shared with Bernard Derrida, if I recall correctly. And it was for his numerous seminal contributions to two-dimensional critical phenomena in statistical physics, including the development and applications of conformal field theory, finite size effects, and percolation. And in 2011, you were given the Dirac Medal and Prize by the ICTP, which was together with Bersan and Samolochikov, if I pronounce this thing correctly, I don't think so, for their independent pioneering work on field theoretical methods to study critical phenomena and phase transitions, in particular for the significant contributions to conformal field theories and integrable systems. And the quote continues, the research and the physical implications of their formal developments have had important consequences in classical and quantum condensed matter systems and in string theory. And I could go on and on. He had many visiting positions, so I think it's a great honor to have you here. And today you are going to talk to us about quantum quenches, approach to many-body quantum mechanics. So thank you very much.
Well, that was... so all you need to get from that is that I'm old. Okay. Anyway, it's a great pleasure to be here and to give this colloquium today, and also to be visiting IFUNAM for the whole week and your beautiful campus here. I'm going to be talking about some problems of quantum dynamics. The subject has become of great interest in the last 10 years or so, both from a theoretical point of view and also an experimental one, because experiments have become possible only with the development of new experimental techniques. So I'm going to start off at a pretty elementary level just to explain what a quantum quench is, okay? So let me, first of all though, remind you what we mean by the word quench in the context of a physical system. We also use the word quench in English as to mean quenching your thirst, but that's not quite the usual application in physics. Though we always like to quench our thirst after a colloquium, of course. Anyway, this is an example of a thermal quench, which is the kind of experiment that I used to learn how to do in high school, which is how you make a piece of steel to make it very hard and strong. So steel is basically iron with various impurities in there, and it's the impurities which actually make the iron strong. You want to make sure that the impurities which make it strong are evenly distributed. So what you do is to heat it up so it's actually red hot, and then you quench it. That is, you plunge it into a bucket of cold water. So what a thermal quench is a sudden change in the temperature. And what this does is to freeze the impurities into the positions that they were in when the metal was hot. So if you cooled it very, very slowly, if you didn't do a quench, what would happen is that the metal will go through some kind of a structural phase transition, and the impurities would rearrange themselves so the metal will be brittle instead of strong. So that's an example of a thermal quench. So here I'm contrasting a thermal quench with a quantum quench. Oops, sorry, pressing the wrong button. So here, this is roughly the phase diagram of a typical material. It doesn't have to be iron, it could be a magnet, or it could be all kinds of system as a function of the temperature and some kind of coupling constant G in the Hamiltonian, in the quantum Hamiltonian, which governs the dynamics or the properties of the ground state. So as a function of temperature, if we're at high enough temperatures, the quantum properties are not all that important. This is basically a classical system in which we may have a phase transition of the type that I just described. So the quench that I talked about was indicated by the red arrow there, where we quench from a high temperature above the phase transition to a temperature below the transition. But we could equally well use the term quench to describe a quench from the high temperature phase to the critical temperature, or below the critical temperature to the critical temperature. These would all be examples of thermal quenches. Now, this is an example of a classical finite temperature phase transition, but we can also have things which are called quantum phase transitions, and they happen basically at zero temperature, or effectively zero temperature, very low temperatures, when the system is in its ground state. And they occur not as a function of the temperature, but as a function of some coupling constant G in the Hamiltonian. So there may be a particular value of the coupling constant Gc at which the energy as a function of G becomes singular, and this will be an example of a quantum phase transition. So just as we can have thermal quenches either going through a thermal phase transition or to a thermal phase transition, we can have quantum quenches where we instantaneously, or as instantaneously as we can, change the coupling constant either from one phase to another or from a phase to the critical point. So the whole point about the word quench, though, is that you do it suddenly. And that means that the system is out of equilibrium. This should be contrasted with what happens if you make an adiabatic change, which is a slow change. In that case, if you very, very slowly change the coupling constant G, the system would more or less stay in its ground state as a function of G. And so we're going to be exploring the dynamics that happens when we instantaneously change G. In the particular examples that I'm going to be talking about, we're going to be looking at this blue arrow here, where we change G from a phase above the critical value to the critical point, and we're going to watch how the system evolves as a function of time. Okay, so actually, this is an old problem, obviously. Looking at a quantum system which is out of equilibrium, and but it wasn't studied theoretically very much for the reasons that I will explain very soon, until we actually wrote this paper, this theoretical paper. You can't read it there, but it was in 2006, so about 11 years ago now. And this was the first paper where we coined the term quantum quench. So we only coined it because it sounded good, you know, quantum quench. It sounds really good. And just as a sociological comment, if you ever manage to write a paper and you introduce a term in it which sounds good, which rolls off the tongue like quantum quench, you know, then lots of other people will use the same term. Okay, so this is always a good idea. So here is a screenshot from the archive, which I took a couple of days ago, which is a search for all the papers that contain the word quantum quench in their titles since then. And as you see, it's about 420. So in the last... So when you... Not actually in their title, but in their abstract, I'm sorry. So even though the idea of a quantum quench was around for quite a long time, the name actually stuck then. So once again, just to review what is the difference in detail between a thermal quench and a quantum quench. In a thermal quench, what happens is that the dynamics after the quench becomes normal relaxational dynamics dominated by slow diffusive coarsening after you've made the quench. So if you wait for long enough, those impurities in the steel will eventually, maybe on a very, very long time scale, diffuse around towards the new equilibrium state. However, in a quantum quench, the dynamics is very, very different. The important thing about a quantum quench is that the system evolves according to quantum mechanics. That's obviously obvious, but the main thing is that over the time scales that you measure it, the system is effectively isolated from its environment. So the system is evolving according to some kind of Schrödinger equation without any kind of contact with its environment. So it's governed by a local Hamiltonian. We will see that a local quantum Hamiltonian. We will see that the kinetics is typically ballistic rather than effusive. The important thing is that because it's not in contact with its environment, the energy is conserved, as are other quantities which commute with the Hamiltonian. And the important thing is that pure state, if you start with a pure state, with a pure quantum state, because you are evolving unitarily with the Hamiltonian, pure states remain pure states. So there is no sense in which the whole system reaches thermal equilibrium or any other kind of equilibrium. It's actually in a pure state, and in no sense is the whole system in equilibrium. Nevertheless, we will see that there is a sense in which these systems do equilibrate. So, but that's a slightly more subtle question. Now, the reason that this problem was not studied very much in the theoretical literature up to about 2016 was that when you look at these kind of problems in conventional solid state physics, the microscopic timescales involved are much too fast, and also the coupling to the environment, for example, other degrees of freedom like phonons, inevitably introduces incoherence. So in traditional solid state systems, it will be very hard to actually observe these kind of things. But in ultra-cold atoms, all of these problems can actually be overcome. One thing is that the interactions are much weaker, which means that the microscopic timescale is longer. We can almost instantaneously switch the interactions, and over easily measurable timescales, the system can evolve coherently, unitarily, according to the laws of quantum mechanics. And another plus is that in many cases, a direct imaging of the observables is actually possible. So I'm going to talk about one particular type of experiment just as an example, just to show you what can be done. And actually, that is now a fairly old experiment, which was done in about 2002. So these are rubidium atoms, which are trapped in a one-dimensional optical lattice. So this is the picture of the potential here, and we have, roughly speaking, one rubidium atom per minimum of this optical lattice potential, but the potential can either be very, very strong with very deep wells, in which case we get one particle trapped at each site, or we can have a very shallow potential, in which case the hopping of atoms between sites is important. So these atoms, these rubidium atoms, are bosons. So they are. This is modeled by what's called the Bose-Hubbard-Hamiltonian, which is a boson variant of the usual Hubbard-Hamiltonian, which is used to model electrons. So these are annihilation and creation operators for these bosons at each site J. J labels the minima here, and T is a hopping parameter, and U, this Hubbard U, you notice A dagger A is, of course, the number operator, and if it's 0 or 1, the U doesn't have any effects. So what this does is make it very unlikely that there's more than one atom at each site. And we're interested in basically the low temperature behavior, that is what happens near the ground state. Okay. So everything's just going to be a function of the ratio G, which is U over T. And if U is much bigger than T, it's the picture I've drawn there, which is a Mott insulating phase. It's insulating in the sense that there's no transport of particles. If U is much, much less than T, the hopping terminates as I've drawn here. And because these are bosons, this is in fact a one-dimensional superconducting phase. So there's a critical value of G called GC, which is an example of one of these quantum critical points that I told you about. And we're going to be interested in a quench from G much bigger than 1, that is, we're going to take G much larger than 1, so we're in the insulating phase, and we look at very low temperatures, so we're almost in the ground state here, and then almost instantaneously quenching G to the critical point. So that was what was done in these experiments, and I thought I should, as a theorist, show you a very diagrammatic view of the apparatus. And I'm sure there's more people in the audience know more about this than me, but basically you can use holography, not the kind of holography that the high energy theorists talk about, but real holography, to actually either create the optical lattice here or to create the trap here. And the nice thing about this system is that once you have done the experiment, you can actually use the same system run backwards to do the optical imaging of the atoms. So don't ask me any more questions about this because I won't be able to answer them. But I think it's always very interesting when you look at a diagram of the experiment and then you actually walk into the lab and it looks so much more complicated. Anyway, so the experimental protocol is to, as I said, aid diabatically. That is, you try and slowly change things. That is, raise the barriers very slowly so that you're pretty much sure that you're in the ground state of the system with G much larger than 1. Then you instantaneously quench the barrier height to round about G. Then you let the system evolve for a time t. Then you want to observe the state. So you want to observe how many particles are at each site. And there might be 0, there might be 1, there might even be 2, rarely, okay? So the way that you observe this is to then instantaneously increase the barrier height, which actually freezes in the particle numbers nj. And of course, because this is quantum mechanics, every time we do this, we get a different answer each time. And then we can read off the we can read off the number of particles at each site essentially by fluorescence imaging. And there's this little quirk here which is not important, which is actually, well, important experimentally, that when you read this off, then you actually can excite the rubidium atoms, and if the if Nj happens to be even, then they can form molecules and escape the system, so that you can actually only observe whether the number of molecules at the number of atoms at each site is even or odd. But usually it's 0 or 1 anyway. So okay, so this is the data that was published by these people in 2012, and I've rotated it on purpose so that I have time running upwards, because in the rest of my talk, or most of the rest of the talk, time is going to run vertically, space is going to run across. Okay, so what this is these are curves of the correlation functions, and it will be the density correlation functions, except that we can only measure the parity, okay, -1 at the end. And so X measures a lattice site, what I called J before, and we're looking at the correlation function, the density correlation function of points separated by a distance d, and also at the same time t. So what you can actually see here is that at time 0, then you have this correlation is small, and what you see is this kind of wave moving across here. Okay, and this is an example of this ballistic propagation that I told you about. You also see something interesting, that is, before this wave goes through, the fluctuations are quite small, but after the wave has gone through, they're sort of bigger, okay? And this is a little hard to quantify here, but this is going to be consistent with what we're going to actually say, that after this wave has gone through, after this ballistic propagation has gone through, then the energy that has been dumped into the system effectively thermalizes it, and these, what you're seeing here, are effectively thermal fluctuations. Okay. Any questions so far, by the way? Okay, so that's pretty much all I'm going to say about experiments, because I'm a very theoretical theorist. What I try to do is to look at idealized versions that we can actually solve analytically. So you can, of course, it's not hard to actually, well, it's actually relatively hard, but you can take this Bose-Hubbard Hamiltonian, put it on a computer, but it's not that easy, because you're not just finding its ground state, you're actually doing quantum propagation. So you're trying to solve the Schrödinger equation for a large number of interacting particles, and that rapidly becomes extremely hard. So anyway, the idealized setup here is that we're going to once again prepare some extended quantum system in a pure state. We're going to assume it's translationally invariant. An example, so our pure state is going to be called psi 0, our initial state. And for example, we would like this to be the ground state of some initial Hamiltonian. And then the quantum quenches that we change the Hamiltonian H0 instantaneously into the Hamiltonian H. And in fact, psi 0 is so H doesn't commute with H0. Psi 0 is not an eigenstate of the new Hamiltonian H. And in fact, we're going to look at what's called a global quench. And a global quench is when this state actually has an extensive energy proportional to the volume above the ground state of H. So we're actually dumping in a bunch of energy compared with the ground state of the new Hamiltonian. And it's an extensive amount of energy. Okay. Just as an aside, we will assume that H is translationally invariant and has no disorder in particular. So there's a whole other field which has arisen since this, called many-body localization, which is when you have interacting Hamiltonians with disorder, and then you can get other interesting effects where this ballistic propagation that I'm talking about doesn't actually happen, and indeed all the states are actually localized, not just in the ground state, but all the eigenstates of the Hamiltonian are localized. So that's a very interesting new field, but that's not what I'm going to be addressing here. Okay, so the kind of questions that you would like to ask and answer are, for example, how do correlation functions and things like quantum entanglement evolve as a function of time? Okay, how do they change as a function of t? Do they ever become stationary? Now, you can only ask this question for a subsystem, because I told you that the whole system remains in a pure state, so it certainly doesn't become stationary. But you can ask the question about a subsystem, which is small compared with the whole system, or maybe not small, but that could in principle become stationary. That is, the correlation functions could. And if it does so, then you can ask the question, what is this stationary state? Is it thermal? How is it approached? Another set of questions that you can ask is, what about the quantum entanglement between this subsystem and the rest? How does this evolve? We actually start with a state which actually has very low amount of quantum entanglement, but we will see that as we evolve it, the quantum entanglement actually increases. If we consider a large but finite system, does the initial state ever recur? That is, can we get quantum revivals? And the last thing is sort of more technical, more theoretical. If the system is integrable, and there are many examples of one-dimensional Hamiltonians which are integrable, and we tend to actually focus on them because integrability means that we can solve them. So, but in terms of the time evolution, it means that for an integrable system, you have an infinite number of conserved quantities which commute with the Hamiltonian and each other. So surely that's going to affect the dynamics somehow. So how does it affect the answer to these questions here? So these are the kind of things that we're going to try to actually address. And yeah, question.
Is, from an experimental point of view, is it easy to access the amount of entanglement between the subsystem and the rest?
No, it's actually very hard to actually measure entanglement. There have been examples that I know about recently. You essentially have to prepare two identical copies of the state, and then you can measure a particular way of measuring entanglement and look at the correlations between those. But that only works for small systems. So it's been done, in the cases that I know, it's been done for trapped ions rather than ultra-cold atoms, but in principle it could also be done for ultra-cold atoms, I think. And it's been done only for systems with 4 particles, 6 particles, and so on. So I think quantum entanglement is very useful theoretically because it gives us some ideas about what is the nature of the quantum state, and it also tells us how we can, what kind of numerical methods we want to actually develop, things like matrix product states, density matrix renormalization group. Those things work because the quantum entanglement is low. And it's precisely actually because, maybe I'll mention this here. Yes, I said here that the numerical methods are difficult but not impossible. And the reason that they're difficult is precisely because the entanglement increases. Okay. So anyway, we tend to use integrable models because we can actually solve them. So they can be integrable lattice models, quantum field theories. I'm going to describe some work that we did on conformal field theories. Don't worry, you won't have to know anything at all about conformal field theory to understand our results, I hope. And more recently, people interested in holography have used the ADS CFT correspondence to study what happens in these particular kinds of, when you do a quantum quench in a theory which has a gravitational dual, but I won't talk about that at all here. Okay, so as I say, this is a rather busy slide, I'm sorry about this, but we actually studied this now about 10 years ago, in the case where we're in 1 + 1 dimensions, that means one space dimension, one time dimension, we start with a state with very short range correlation length, correlations and short range entanglement, and we quench to a critical point, that is our Hamiltonian is going to be a conformal field theory Hamiltonian. The reason for that is that we know that conformal field theory describes the universal low energy behavior of gapless, of in particular this Bose-Hubbard model at the critical point. So we're actually going to use this model to because conformal field theory is one of the most integrable of integrable models. But all the results I'm going to describe actually depend upon some very general properties of conformal field theories. They don't depend on the fact that we're looking at a particular CFT, and most of the results can be attributed to the fact that the excitations or the quasiparticles all travel at a constant speed either to the right or the left, and there's no left-right scattering. Later on in this talk, I'm going to briefly describe what happens when you relax that constraint and you include left-right scattering. So the results can all be interpreted. So there's a lot of analysis, there's a lot of equations which you can all find in our papers, but it turns out that the results can all be interpreted in terms of this simple quasi-particle picture, which I'll try to explain in the next few slides. So the results, though, before we come to the explanation, first of all, if we just look at one-point functions, expectation values of just local quantities like the local, well, not the local density, because the density is conserved, so some other quantity which is not conserved, then typically they decay exponentially in time. However, if you look at correlation functions, then they initially decay in time, but then they become stationary once the interval x1, x2 that you're measuring between falls inside what's called a horizon. So we call this the horizon effect. So this green line represents the line from x1, represents the line between x1 and x2 evolving as a function of time. So this is a space-time picture. So initially they're uncorrelated and they remain, so the operators are at the ends of this line here, the observables, and they remain uncorrelated until this line falls within a horizon. That is, if you track back, there's a kind of light cone here, and if they fall within this light cone, then they immediately become correlated, almost instantaneously. And then as you evolve for later times, the correlation function doesn't change. Okay, so it's a very simple result. Moreover, once you actually fall inside the light cone, the correlation functions are indistinguishable from those at finite temperature. So you could ask what temperature, because there's no temperature here. We actually started off in the ground state of another Hamiltonian. We dumped a bunch of energy and there's no temperature there, but there is, because if the system were in thermal equilibrium, if it were, then there will be a correspondence between a certain temperature and a certain energy density. So the energy is conserved, right? So there's a certain energy density there. That corresponds to a certain temperature. And what we're saying is once the correlation once this interval falls within the horizon, the correlation functions are just as though this interval were at equilibrium at that particular temperature. So this is an example of thermalization in this case. And you can actually show that the reduced density matrix is exponentially close to a thermal one. The other thing is, and I haven't defined this, so this is something for the experts, you can, a measure of the quantum entanglement between the interval and the rest of the system is this so-called entanglement entropy, and what you can show is once this interval falls inside the horizon, then the entanglement entropy is the same as if we measured the usual thermodynamic Gibbs entropy at this particular temperature. So these results are very, very simple. They're almost too good to be true, actually, and I'll explain why they're not actually true. But they're almost true, anyway. Yeah, question?
What is a subsystem?
Excuse me?
Reduce, sorry, I can't speak. You may have reduced density matrix, but I don't understand what is A. It's a subsystem.
Oh, A is this interval, right? Okay. A really means all the degrees of freedom in this interval. Okay, so you take the density matrix of the full system, which is in a pure state, and you trace out everything else, and that gives you rho A. Okay. Okay, so the quasiparticle picture, which sort of explains this, is illustrated here and in the next couple of view graphs. As I told you, in a 1+1 dimensional CFT, all the excitations travel at a constant speed. And so this is once again a picture of time versus space. And the initial state here at time t equals 0 has a finite energy density with respect to the ground state. So it's the source of these quasiparticles. But because the entanglement and the correlations are very low in this initial state, you can think of it as a source of entangled pairs of quasiparticles, one of which goes to the left, the other goes to the right. These are precisely like these Einstein-Podolsky-Rosen pairs of quasiparticles. They are like entangled photons that EPR discussed in the context of the EPR paradox. And they're entangled over a very, very short distance here, depending on the energy density of the initial state. So what do these quasiparticles do? So the idea is that if we're just measuring the expectation value of some local operator, so if we're looking at the value of phi at a particular point x as a function of t, this particular observable, it might be like a quantum spin or something, is continually being bombarded from the left and the right by these quasiparticles. But this is like incoherent radiation because they're all coming from different points in the initial state. So the spin is just flipping at random times like a Poisson process, and its expectation value then is going to decay exponentially. Okay, so that's one point. The next point is if we look at the two-point function. Okay, so this is the first in a series of 3 graphs where I will show you what happens at early times, at intermediate times, and at late times. So at early times, what happens is that here is this interval, here are the operators at the ends of it, here are these quasiparticles, and because the only correlations are due to these correlated quasiparticle pairs, it's not possible for a left mover to hit this and a right mover to actually hit this at this early time. So the 2-point function is just a product of 1-point functions. They're not correlated at early times. However, if we look at the entanglement between this region A and the rest of the system, the entanglement is due precisely to pairs like this, where the left mover where the right mover has hit the region A and the left mover has hit the region outside A. This is going to cause entanglement between here and here. And you can see, I hope, that if you say that the entanglement is just proportional to the number of such pairs, one of which hits A and the other one does not hit A, then the entanglement is going to grow linearly in time, okay? Because the number of such pairs, so the pairs here don't contribute, but this one does and this one does. Then we're going to evolve in time up to the point where, just the point where this interval falls within this horizon here, okay? Then just at that point, the 2-point function has been a product of 1-point functions decaying exponentially, but just at that point, they become correlated, and they become correlated precisely due to this quasiparticle pair here. And because it was exponentially decaying in t, and because t is proportional to x1 minus x2, that's also exponentially decaying in x1 minus x2, and the entanglement entropy was proportional to t just at this moment, and it's therefore x1 minus x2. Then we evolve further. Now it's completely within this horizon. What's going to happen now is that the correlations aren't going to change because there are no quasiparticle pairs available because they're all moving outside here. They can't correlate phi and the two phis anymore, so the correlation function doesn't change. It freezes at this particular value, decaying exponentially, and the entanglement entropy does not change either. Okay. So this is this very simple quasiparticle picture. It's obviously very much dependent upon this idea that the particles all travel at a constant speed and there is no left-right scattering. That is, in this picture here, when this particle hits that might interact here, then you would expect some kind of phase delay here or maybe some inelastic processes here, and that would sort of tend to destroy this picture.
At what point you mentioned that the quasiparticles move quasi-classically?
They move quasi-classically, and I didn't prove that, but actually all the calculations that we did are perfectly good analytic calculations. This is just a physical interpretation. So what you can, if you assume that, so what we're assuming is that the only quantum part of this whole process takes place here, and that once they've moved apart, they are moving quasi-classically and just carrying their entanglement with them, like EPR pairs do. Okay, so this simple picture explains the analytic results that we get. Okay, that's all I'm saying. Okay, so how general is this? Well, here's an example worked out numerically for an XXZ spin chain, which either in the integrable case, because usually with the nearest neighbor interaction it's integrable, but you can add a next nearest neighbor, so it's non-integrable. And now time is running downwards. Excuse me, but you can clearly see this ballistic motion actually, and it's a bit weaker here in the non-integrable case, because what happens is these states actually decay, so this thing gets broadened. There's a general bound in all these spin systems called the Lieb-Robinson bound that says that correlations can't spread faster than ballistically, and it suggests that they do actually propagate ballistically. I should also say that in experimental systems like the one I mentioned, this has been looked at much more closely, and one also sees this ballistic propagation. The interesting thing here is, though, that this XXZ spin chain in the region of parameters that they looked at also has quasiparticles, but it has bound states. And what you see clearly here are the propagation of two different kinds of particles. One are the original particles, which travel faster. The other ones, which travel more slowly, are actually bound states of these particles. So this gives you a direct way of imaging the spectrum of the Hamiltonian, actually. So the question is this real thermalization? Okay, so we could probably argue all day about this. Everybody probably has their own idea about what thermalization is, that you need to have a heat bath, things need to be ergodic, things need to sample the space and so forth. This is not what is happening here. First of all, just to get rid of a simple point, is that because this model is integrable, we would expect not to go to a Gibbs ensemble, but some kind of generalized Gibbs ensemble where the reduced density matrix has this form where HK are all the conserved quantities. This in fact happens here. However, the strange thing about this so-called thermalization is that it takes place in a time that it takes for a quasiparticle to cross the subsystem. It happens in a very short time, not like the usual thermalization that you learn about. So this thermalization is not the usual kind, and it happens as a result when you looked at closely in model systems. It happens as a consequence of quantum interference, actually, and in the literature it's sometimes called pre-thermalization. So what happens is that the system goes into this almost stationary pre-thermalized state, and it stays in there for a long time, especially if the system is close to integrable, and then eventually you get, quote, true thermalization. Okay, how are we doing here?
5 more minutes.
5 more minutes. Okay, I can talk a little bit about quantum revivals. If you, in this quasiparticle picture, if you have the system in a finite box, so either periodic boundary conditions or reflecting boundary conditions from the walls of the box, in this quasiparticle picture, if you wait for a certain time of order L, where L is the size of the box, the initial state is going to reconstruct itself exactly. And one way to quantify this quantum recurrence is in terms of this return amplitude. That is, we start with our initial state, we evolve it with the Hamiltonian, and look at the overlap with the initial state. So there's a lot of structure here, and just to show you a quick glance of a theoretical calculation of what would happen in a quantum spin chain called the Ising spin chain. This is the return amplitude, but it's the logarithm of the return amplitude. So what happens is that it decays very, very quickly. And here's the quantum recurrence here at a time when 2t is L. So it goes back to what it was it goes back to 1, but you see all this kind of interesting structure in between, which when you make the system bigger gets even more interesting. So there's a lot of interesting mathematics here. You actually get a peek at every rational value. It would be not that you could observe that experimentally, but this is a theoretical calculation. So I'll just move on and say what we expect to happen in a more realistic model where things don't always travel exactly at the same speed, where the model is not necessarily integrable. So we can study this theoretically by taking our conformal field theory Hamiltonian and adding some other operators here, which we can characterize as operators of conformal field theory. Usually, if these are what are called irrelevant operators, they have no effect on the quantum phase transition, which takes place in the ground state, in the low energy states. These irrelevant operators don't affect the critical behavior. But when we do a quantum quench, then we're dumping in a finite energy density, so we're exciting states which are nowhere near the ground state. So one needs to have some way of quantifying how changing the Hamiltonian is going to modify the results that I already told you. This is a very hard problem in general, but there is one limit in which we can actually do this, which is to include what's called left-left and left-right scattering. So this is once again a bit more for the experts. In a field theory, we can write the Hamiltonian as the spatial integral of the energy density, which is of the Hamiltonian density, which is the time-time component of the energy momentum tensor, which in a CFT splits into left movers and right movers. If we take the perturbing Hamiltonian as being the integral of the square of these objects, this introduces scattering. And this particular perturbation can actually be treated analytically. And there are two main effects. One is that basically whenever you have the square of an operator, the first thing that you try to do is some kind of mean field approximation or Hartree type approximation, where you approximate the square by its expectation value times the operator. So this is just the energy density, which goes like the effective temperature squared times the energy density. So what this perturbation is doing in this crude approximation is to just add a term in the Hamiltonian which is proportional to the Hamiltonian itself. So you're just rescaling the Hamiltonian. And rescaling the Hamiltonian is just like rescaling time, because in the evolution it's e to the minus iht. So you rescale time, but you don't rescale space. So that means that these things that were all these quasiparticles that were traveling at a certain velocity, the velocity gets renormalized, and the change in the velocity, the change in the propagation speed depends, however, on the energy density of the initial state. So you get a propagation speed which depends on the initial state, which it didn't in the pure CFT. So this is also observed numerically and experimentally too, that if you change the initial state, the speed of propagation actually changes. You can understand this because in the quasi-particle picture, once you have scattering of quasi-particles, once a left mover meets a right mover, they're going to scatter. There's going to be some time delay depending on whether the interaction is attractive or repulsive, and that's either going to slow things down or speed things up. So the second effect is a bit more complicated to explain, but one thing that you can do in quantum field theory, whenever you have the square of something in the action here, which we've got here, is to undo it by a Gaussian integral transformation here. Whoops. And so this is just a mathematical convenience, but the thing that couples to the energy momentum tensor in the action is just the metric. So it's as though we had a theory in a random metric with local correlations. So the effect of the right-left scattering is just as if we were propagating in a random metric with short-range correlations. And that has the effect of that the light cones actually get broadened. It's as though the light cones actually execute Brownian motion, random Brownian motion, and they get broadened like the square root of time. So you still have light cones, but they're spread out. So this is what we expect the effect of this scattering to actually do, and this is what is observed in these numerical things. And when we look at quantum revivals, they get broadened too. This is so we don't have perfect quantum revivals. The amplitude decreases actually as a power law, and they get broadened, and eventually they spread out so much that you have no revivals at all. So to summarize, quantum quenches give a new and exciting way of probing of quantum dynamics in many body systems. They can be realized in experiments, and there have been more experiments since the one I showed you. The basic effects we're talking about are this horizon effect, that you get basically ballistic behavior, but maybe the propagation speed depends on the initial state. We have a new way of thinking about what we mean by thermalization in quotes. That is, we can make states that look thermal without having to wait a long time. This, by the way, also gives us an interesting way of making highly entangled states, which you might want to use as a resource in quantum information theory. There's this issue of integrability versus non-integrability, and one expects in these integrable models or almost integrable models to see quantum revivals in small systems. So I could say a lot more. As I told you, since we wrote our paper, there have been 400 and something other papers written on the subject, all examining it from a different point of view. But I hope this talk has given you some inkling of what the subject is about. So I thank you very much.
Thank you for that. Time for questions. Are there any questions?
So these quasiparticles, like given a Hamiltonian, can you somehow extract the nature of can you calculate the quasiparticles?
Well, if you have an integrable model, then actually something that's usually a model solvable by the beta ansatz, and the beta ansatz precisely tells you what the quasiparticles are, what their quantum numbers are, what their dispersion relations are, and so on. So depending on the model, the quasiparticles will be different.
Start being entangled, or is it?
Well, if you're in this, I'm always starting from this initial state with very low entanglement, so that only particles that start close together are entangled. If I started from a highly entangled state, then it would be, then the quasiparticle picture would still be true, but I wouldn't have these results like the horizon effect and so on. So I'm talking here about a quantum quench from a highly disordered phase or a phase with very short-range correlations and entanglement to a critical point. You can do all kinds of other things. There are interesting things that you can get when you quench through the critical point, for example, from a disordered phase to an ordered phase, for example. But then the results are going to be different. Yeah?
Which is the Hamiltonian that you use? I refer to this Hamiltonian, the conformality theory Hamiltonian.
Okay, so the results that I was describing are true for any 1 + 1 dimensional conformal field theory. They are very general. They just depend on certain analyticity properties of the correlations. But they've been checked in particular models like the Hamiltonian that represents the scaling limits of the Ising model, for example, because that's a free fermion model and you can solve it exactly.
In the experiment you discussed about in the first slides, it's not about the technical details, but you say you first start with a high potential barrier and then you quench it to the critical limit, and then you rise it again very quickly to confine the particles. But isn't that like another type of quench, or not necessarily?
Well, that's how you make the measurement. That's how you project onto. Right. So after the quench, after you've made the quench and you have evolved in time, the system is in a pure state, which is in a linear superposition of all kinds of particles, different numbers of particle number. The act of making the quantum measurement is to project onto one of those states, and you do that by raising the barrier. So that's the measurement process. Okay, so it is like a quench, yes. So maybe there's you might make some. There is a sense in making a quantum measurement is a little bit like a quench.
There's another small question. How does one fit finite temperature into a CFT? Isn't like that intrinsically non-conformal?
No, I mean, it's quite easy to consider a conformal field. So you can have the Hamiltonian as the Hamiltonian of a CFT, and you just consider that Hamiltonian at a finite temperature. So you just consider e to the minus beta h, where h is the conformal field theory Hamiltonian. Yeah, it breaks some of the symmetries, right? So it breaks the Lorentz invariance, for example, but there's nothing, but because the theory is conformal, there is no mass scale, so the only energy scale in the system is going to be the temperature. For example, if you consider black body radiation, okay, that's just the photons in this room which are at a finite temperature. then that's an example of a conformal field theory because because Maxwell's equations do not have a mass in them, right? Because the photons are massless. So if you want to ask what is the energy density of the photons in this room, you can use dimensional analysis to say that they have to be like the temperature to the fourth power, right?
More questions? Well, if not, there is food now outside, so we can continue the discussion. So thank you very much for this very interesting.
Thank you.